Yeah, good evening. Today we'll discuss about back EMF. Basically, when you take any DC motor, the working principle is a important thing to understand first, to know about its dynamics. In fact, there is a video of mine in the previous lectures I have given about DC motor principle. If you can see that video, you'll understand how exactly the DC motor rotates, what is the force that is exerted on the DC motor, right? Fine. So there is a very good phenomenon called back EMF phenomenon, or a phenomenon of voltage production in a DC motor, right? So I'll come to the point. So there is a voltage produced by a DC motor. It looks strange, even it listens, it sounds to be strange that is there a voltage produced inside a motor? Yes, you're right, you're hearing right if you're hearing it so. So the motor, a DC motor, is bound to produce some voltage in it, and that voltage is called back EMF. Yes. So what is back EMF? The other name for this is called counter EMF. What is that? Counter. So we'll discuss about what is this EMF. EMF is nothing but, in our usual language, we call it as voltage, right? So there are different ways of producing voltage. And if you want to produce voltage, or if you want to have EMF in anywhere, even suppose if you take any generator or AC generator or DC generator, has only one principle, that there should be a conductor and there should be some magnetic field, and this conductor should cut the magnetic field so that it can produce EMF, right? So what should happen? There should be a conductor and there should be magnetic field, and if this conductor is made to rotate in the presence of the magnetic field, then there will be a EMF produced in the conductor. This is how you can know about the production of EMF. Now, the point is how that voltage is produced in the DC motor. Let us see that, a glimpse of the working principle again, right? So I took the working principle with two of the poles on the both sides. Two of the poles on the both sides. This is North Pole and this is South Pole. Shit, sorry. Might be it is not so good for right. It's okay now. Fine. These are the number of these are the two poles that I have taken, North Pole and South Pole. Maybe this can be an electromagnet having some coils on either sides. Fine. Now, when you have a coil and you'll have a you'll have a magnet, you'll have a flux, right? And what did you do? You keep a conductor in a armature frame, right? Right? Fine. This is conductor A and this is conductor A dash. Fine. So what happens? There will be two flux components. One is phi m this side, and there will be a flux here inside of it. If the current is going inside into this conductor A, this flux is phi A, and this flux will be, if the current is coming out through this conductor, this flux will be like this, phi A dash. I explained in the video that I have delivered on DC motor working principle that here on the top of the conductor, these two flux components will have an interaction. These two flux components will have an interaction, and that two interaction will be these two flux components will aid each other. Then what will happen? There will be a more number of flux lines will be accumulated on the top of conductor A, and similarly here at the bottom of conductor A dash, you'll have more accumulation of flux lines. So the flux lines, the blue lines what I have indicated initially, are the flux lines phi m which are going from north to south. But when you connect a battery to the armature conductor and give some current in such a way that A is taking the current inwards and A dash is taking the current outwards, then there will be an interaction of flux phi m and phi A will be interacting on the top of conductor A. You will have aiding nature, and at the bottom phi A will oppose phi M, and because of that very less amount of flux lines will go at the bottom of the conductor A, and because of the same reason very less amount of flux lines will accumulate on the top of conductor A. Anyways, because of the more accumulation of flux lines, these flux lines will tend to come back to its original state. It tries to be like a straight line because of its elasticity property. These flux lines will impose a force on conductor A, thereby what will happen? The force will be generated on the conductor A from the top, I mean from its above. So this is a force which is acting on this conductor A, and there will be another force acting on conductor A dash. That force will be pushing it up. So thereby what happens? The armature conductor rotates in an anti-clockwise direction. This is what is a working principle. Okay, so I was so rapid, I mean so fast in doing this working principle. You know why? Because already I have taken a lecture on this in some other videos. So fine, what happened now? When I give some voltage, there was a flux here. Already there is a flux in the mainstream flow of the magnetic field. So these two flux components have an interaction. Because of that, more flux lines are at the top of the conductor A and more flux lines at the bottom of conductor A dash. This will try to push the conductor A down and A dash up. Because of that, the armature now rotates. Armature is rotating, which means the motor is rotating in the anti-clockwise direction. Fine. What happens now? The motor is rotating. Nowhere it is seen that there is a voltage production, but still you need to concentrate on one point here. When the motor is applied or imposed with a force F is equals to BIL sine theta, it is started rotating, right? It started rotating. The moment when it starts rotating, what is happening? Can you observe? This conductor A is cutting the flux phi M. Already the phi M lines are here, right? This conductor A is cutting the flux lines, which means what is happening, my dear? Faraday's first law is getting satisfied. Faraday's first law is being, satisfied here, is implied, in fact. So based on that, you can say that in conductor A, because it is cutting the flux and it is satisfying Faraday's first law, you can say that conductor A will have its EMF produced. I mean, EMF is produced in conductor A. Similarly with conductor A dash, if you take 100 conductors, all the conductors are being moved on the armature, right? So all the conductors are cutting the flux lines. Because all the conductors are cutting the flux lines, there will be EMF produced in all the conductors, and this EMF is called back EMF. And it is denoted with EB. Right, so motor is generating some voltage. Motor is generating some voltage. But the point is that why is it called a back EMF? Why is it called a back EMF? It is because of Lenz's law. In other videos, I have explained about Lenz's law, effect of Lenz's law in an induction motor, three-phase induction motor. Now, effect of Lenz's law in DC motor is that whatever the voltage that is produced in the motor, when the motor is derived, I mean driven by the force, that EMF will oppose the main voltage. Something like this will oppose the main voltage. Let's say backward arrow, put VT, which means VT is a supply voltage given to the armature conductor. Maybe consider that VT is the voltage that is given into the armature conductor, right? So EB is opposing VT. EB is opposing VT, right? And now when EB is why EB is opposing VT? I am saying it is because of Lenz's law. How is it so? What is Lenz's law? Lenz's law is the one which is seen in all the magnetic circuits, magnetic coils, right? What is Lenz's law? Lenz's law can be defined as effect opposes the cause of its production. Effect opposes the cause. What is effect? Effect here is production of production of EMF in the armature conductors is called effect, and the reason for this effect is the supply voltage. Am I right or not? We'll go back to this what is that hierarchy from one by one. So what is the reason for the back EMF? The reason for back EMF because there is a force applied on the conductors and the conductors are moving. That is the reason. What is the reason for this force? Because there is a current given, there is a flux, in fact flux phi A and phi M are interacting. Because of that the force is produced. How phi A is generated? How phi A is generated here in the armature conductors? It is generated or it is produced, it is induced in the armature conductors because of the supply voltage what you apply to the armature conductors. So EB is the effect and the reason for its production is Vt. Hope you are understanding me. Now according to Lenz's law, EB should oppose what? EB should oppose Vt. That is what is happening. So as to oppose that, this EB, whenever you draw any circuit diagram of a separately excited motor or a shunt motor or a series motor, let's say I take a separately excited motor, right? So whenever you draw a motor circuit like this, equivalent circuit like this, right, you indicate EB here and then you write an arrow mark. This is your Vt, this is your EB, which means EB is opposing the main voltage. EB is opposing the main voltage. This is how you can understand about what is back EMF, right? And the direction of back EMF, why is it opposing, is because of Lenz's law, right? This is how we can understand about counter EMF, right? And in other discussions, I mean in other sense, back EMF is the reason, is one of the important aspect here to make a DC shunt motor or a DC motor a self-regulating motor. What is it, sir? So you may ask me a question, what is it, sir? So something like, see, if I have to take an equation for IA, so IA equation can be taken as Vt minus EB divided by RA. Am I right? There are two voltages and there is a resistance for the armature. So I can take the expression for the current, armature current, as Vt minus EB divided by RA. Right. So EB, what is EB again? Back EMF, right? So back EMF, see, always your RA is constant with respect to load. With respect to load, whether you increase the load or decrease the load, RA will not change. So at no load or full load, RA will remain same. Then what will change? What will affect the current? At no load, the EMF will be very high. Thereby, you will have very less current. Why EMF is very high? As I told here, back EMF is nothing but the EMF produced in the DC generator. I mean to say, you can take the same equation. So from that, you can get that phi Zn by 60 into P by A, where phi is the flux per pole, Z is the number of conductors, and N is the speed at which the armature is moving or the armature conductor is rotated, P is the number of poles, and A is the parallel paths taken in the armature winding. That's fine. If I take the equation here, I will get EB is proportional to phi into N. What is this phi? Phi is constant for a separately or shunt motor, right? If it is a series motor, we'll have a different discussion. But as of now, for separately excited motor, you can take phi is constant, and thereby EB is proportional to N. EB is proportional to N. So at a very less load, I mean at no load, the motor will run very freely. It's a free running condition, right? It's a free running condition. When under no load, when it is freely running, the speed of a DC motor will be very high. It's equal to the rated speed. Then EB will be very high because EB is directly proportional to N. So when EB is very high, then you will have IA very less. So what is happening here? IA, the current drawn capacity or the current drawn by the motor is dictated, or else it is determined by the amount of EB. And under no load you have more amount of speed, more speed and more EMF and less current. Under no load the current drawn by the motor is very less. It is just to satisfy the losses and the magnetic field production there inside the, just satisfied the losses, armature copper loss and core loss, right? And under full load the speed is going to be very less. Because of the speed is very less, your EB will be very less. Because EB is less, you can see out of this equation, when EB is very less, you'll have more amount of current drawn by the motor. That's why this particular EB is the one which allows the DC motor to be a self-regulatory or self-regulating motor. The current drawn by the motor is regulated by the back EMF. If there is no back EMF, then imagine this equation. It depends on the armature resistance. Am I right? It depends on the armature resistance. So if there is no load or full load, it doesn't make much sense on IA, right or not? So because of EB, because of the concept of this back EMF that is existing there inside a DC motor, you can say that the DC motor is a self-regulating motor. Hope you got the right understanding of what is back EMF. Have a nice time. Thank you.